This is Module 15, Lesson 2. This is going to be our more difficult lesson out of this module. In the end, there's basically two types of things that we need to be able to answer. I'm going to work plenty of example problems as we do this, which is going to make it a little lengthier. So, we're talking today about reversible reactions and equilibrium. We are actually talking about equilibrium this time. So first of all, let's look at reversible reactions. We have been looking at reactions that only have one arrow. Somehow I've lost my pen. We've been looking at things that only have one arrow that point to the right. So we'll have reactants on the left and we'll have products on the right. Well, today we're going to look at something that's called a reversible reaction. And so you can read the definition there. It says that basically the reactants can become the products and the products can become the reactants. When we talk about a forward reaction, we're talking about the arrow pointing to the right. When we talk about a reverse reaction, we're talking about an arrow pointing to the left. So if we have one that can go both forward and reverse, we're going to write it with a double-headed arrow like this. You will commonly see the arrow done this way. I just don't think I had the option to use that in my PowerPoint. So you'll either see two arrowheads on it, or you'll see half an arrow pointing right and half an arrow pointing left. So if we want to talk about this reaction, and you want to talk about SO3, then we'll need to know if you're talking about the forward reaction, then SO3 is a product. But you're talking about the reverse reaction, then SO3 is a reactant. It's just kind of looking at it as something that can be reversible. It can go either way. Okay, from there, let's talk about chemical equilibrium. You should know that equilibrium is any time you have two things that come to be balanced, basically. They come to be equal. And so this tells you that when you have equilibrium with reactions, you have the forward and the reverse reactions happening equally, hence why they're written with a double-headed arrow, because they're going both ways at the same time. It says right here that there's no net change occurring in the actual amounts of the system. So if you think about what we talked about earlier in the year, we talked about like vaporization and condensation happening at equal rates. If we're going to put a chemical reaction inside of this container, how you reach an equilibrium would be to put a lid over the top of this so that nothing can get out. And then if it's trapped inside, you have no net change. Nothing is escaping, nothing is being added. It's just a matter of one thing is turning into the other thing just as quick as, it changes back to the way it was before. The reaction doesn't stop. They balance each other as needed. If you do something to change this, then the reaction will adjust. The best way I know to explain it is if we go back to where we talked about water inside of a container. If we have a container with a lid on it, and we have liquid water inside of this, there'll be little drops of water, little gaseous particles forming up here in the air of the container. And if you go sit this in the sunshine, what'll happen is you'll have the amount of dots will be increasing, like the amount of liquid water that's turning into gaseous water will increase. Well, at the same time that that's happening, it'll also condense and it'll form droplets on the inside of the container. So the faster it's turning into vapor, the faster it'll condense and turn back into a liquid. We're looking at the same idea with reactions this time. The faster that we can make the products on this side, the faster it'll make it turn into products on this side. It'll just basically compensate for whatever you do. Now, there's a couple of other things down here at the bottom about concentrations don't have to be equal. We're not going to be concerned about that. Catalysts, will speed up the forward and the reverse equally. We're really not going to look at that either, to tell you the truth. It's just kind of some fine print to go with this in case someone is wondering. What we are going to look at is what happens when we do something to this system, to the equivalent of with the water, setting it in the sunshine. Like what happens when we tinker with it? How will it react to us? So the basic idea is called the Chateliers Principle. It was a Frenchman, he was a Frenchman, who came up with this idea that if you stress the system, it'll change in such a way to relieve that stress. It's just like if we set the container of water in the sunshine and it makes more gas, then the system will switch up in such a way to deal with that, it'll make more liquid. We have three stresses that we're going to look at. We're going to look at change in pressure, change in concentration, and change in temperature. I'm just going to take them one at a time. Okay, first off, let's look at change in concentration. Here's how this is going to work on my practice problems, my checkpoints, my test, and the final exam. You will be given an equation such as this. So it'll give you the information for the equation. And then it's going to ask you something like, if you add CO2, how does this respond? Well, your responses are going to be one of four things. I'll put them up here. I'll do it in red so you can see them better. First of all, you can say that it shifts left, or you can say that it shifts to the right. Okay? Shift right means it's going to make these things more. Shift left means it'll make the stuff on the left of the arrow more. There's an alternate way to put this, and we just learned it. If you're heading to the left, you could say that it shifts reverse. It favors the reverse reaction. Or you could say for the right that it shifts forward, which means it favors the forward reaction. I guess you could even use those words. You could say that it favors the reverse and it favors the forward reaction. So I'm going to take this one for an example. We're going to walk through all three different kinds, and then I'm going to do tons of practice problems, okay? So if you add CO2, what that means, and I'll use a highlighter here, what that means is we are adding more stuff on the right side. Okay, if we're adding more stuff on the right side, for adding stuff, for concentration, this is pretty simple. If you add it to the right side, then it's going to want to go to the other direction. It's going to shift to the left or the reverse reaction, because if it goes to the right, it's going to make more of all of this stuff. You don't want to make more of all of that stuff. You're adding more on this side anyway. It's going to go the other way. So it's going to shift to this side to make more. So your answer would be it will shift to the left, or it will shift reverse. Now, what if you take CO2 out of it? So what if we actually come in here and we go, no, let's take away CO2. Doesn't say that we take it all away. It could be all of it or a little of it. It's going to want to undo that. Well, if it goes over here to H2CO3, then that's making more stuff on this side. That doesn't help me any. It wants to undo what I did. If I take this out, then it's going to want to make more of it. Well, it makes more when it goes to the right. When it shifts to the right side, it's making CO2 and H2O. So the answer on this one is it shifts to the right or the forward reaction. So for concentration, you basically you undo whatever it does. You shift in whatever way will undo what happened in the first place. Okay, what about temperature? Well, temperature will cause equilibrium to shift, okay? You have to have a reaction that has heat written into it. And it may even say something like 324 kilojoules. It may not say the word heat. It may actually give you an amount of heat. But we just did all kinds of lessons on this. We should understand that kilojoules is heat. I have some facts for you up here that you can read. I'm not going to read them to you. Let's work with the examples here. If you want to write the top stuff down, then give it a pause and write it and then join me again. Okay, there's only two questions that could be asked about this particular one. I could ask you a question about what happens when you add heat, and I could ask you a question about what happens when you take away heat. And those are the only questions regarding heat that I could ask. Okay, if you add heat, where is that at? Well, heat is on the right side. So this is quite like last time. If it's adding to the right, then it's going to want to do the opposite. Then it's going to head to the left. Why would that be? Because when it goes to the left, it uses the heat. If it goes to the right over here, it's just going to make more of it. We need to undo what we have done. Okay, what if we take away heat? If we decrease the heat, if we come in here and we take it away, then what's it going to want to do? The opposite of take away is put back. It's going to want to make more heat. Well, which side of this reaction makes more heat? Well, that would be the right side. So our answer is it shifts to the right or the forward direction. Okay, I mean, at this point, I personally think that these are fairly straightforward. It's just a matter of thinking about which side things are on and how to undo it. Keep in mind, I'm going to do some more examples at the very end, so if all else fails, just keep watching till the end. If you think you have it, you can try the practice problems. If you're a little iffy about this, then I highly recommend watching the rest of the examples. If you take the checkpoint and you bomb it and you didn't watch the rest of the examples, well, I know what you need to do. You need to watch those examples before you take it a second time. All right, let's look at our last one. Let's look at pressure. Pressure is a little different. For pressure, it says it has to be gaseous equilibrium. Okay, see, this one has all gases. If I went back to the one before, I could do it with this one too because I have gas, gas, and gas. What about the one before this? Okay, now this one wouldn't work for pressure questions simply because I have no gaseous equilibrium. I also couldn't ask temperature about this one because we don't know which side takes in the temperature. There's no temperature indicated. So on this one, when we're looking at it, we are looking at this, okay? So the basic idea is this. We know from the mole section that 1 mole of gas is 22.4 liters. And basically, the more volume you have, the more pressure you're going to have, okay? So it says it doesn't matter what size these are, like they all have the same volume regardless of their particle size. That's what this is saying up here. It's the number of molecules or the number of moles that's going to matter. So here's what we're looking at in this one. We are looking at the coefficients in front of each thing. So, okay, grand total here. On the left side, we have a grand total of 1 mole of N2 because there's an understood 1 right there. Then we have 3 moles of hydrogen gas. That adds up to a whopping total of 4 moles on the left of the arrow. We have 4 moles of gas over here. You see I'm getting that 1 plus 3. Now on the right side of the arrow, we have 2 moles of gas. We have 2 moles of ammonia right here. So which side has more moles? The left. What that means is that pressure is going to be higher on the left and lower on the right. You're going to have to do this in order to answer the questions. If you can do this, then it's just like the last 2 examples. If we increase pressure on the system, okay, then we should know it's going to want to do the opposite. If we increase the pressure, it's going to want to decrease the pressure. Well, which side has less pressure? That would be the right side because it's got fewer moles of gas. So it's going to shift to the right or the forward direction. If we decrease the pressure, then what does it want to do? It wants to increase it. You may know that, but if you can't remember this mole thing, you won't be able to answer the question. So if it wants to make more pressure, the side with more moles has more pressure. So it's going to shift to the left. Now, my face-to-face students always have some difficulty with this. They seem to get really mixed up. And I think a lot of it comes down to just simply memorizing some things. On this one, you're going to have to memorize the part about the moles and the pressure. Now, I have one more thing to do with you, and I will do it with you, and then after that, I will go into all of my example problems, so you can continue to, you need to continue to listen until I say, hey, now I'm going to work a bunch of example problems, okay? There's one more thing that we need to do. Before I get to that last thing, if you're having some trouble with this, honestly, if it comes down to it, you could memorize this little chart. I found this somewhere years ago and think it's very handy. I'm not going to spend time going over it. You can pause and you can copy and you can study this. Now, here's our last thing. One of the things that you need to be able to do for the final exam is you need to be able to write what's called the equilibrium product constant. Okay, constant is represented here with the K, and the equilibrium part of it is represented with the EQ. What this does in real life is it's a mathematical equation. If we put concentrations in here, and you're going to see this later, whenever you see brackets like this, what that stands for is concentration. Remember when we worked out concentration in molarity? Like you would see, I can't spell, you would see capital M after something like 3 molar or 0.2 molar. You put those numbers in here. Now, we're not actually going to do that. We're just going to write the expression. This looks crazy, but students always have an easy time of this. It's like once I show you, it seems to be pretty simple. So here's how the formula goes. Okay, the little letters represent the coefficients. All right, the big letters represent whatever substance is in there. Okay, so what you do is you put the products on top. Like we're using this for the forward reaction. You put the forward products on top. Okay, you're going to put whatever is here inside of brackets, and you're going to raise it to a power of the coefficient. And then you're going to repeat that if there's anything else, and then you're going to do the other side. And let me skip ahead here for a second. I don't have any examples right here, so here we'll make up something. So let's say it's this. Let's say it's H2 plus O2 yields H2O. And let's see, that would be a 2 and a 2 right there. So how would we write the KEQ for this reaction? Okay, well, I need to put the products on top. My product is H2O. We put it in square brackets, and we're going to raise it to a power of the coefficient. We're going to raise it to the second power. Now, I don't have a plus in anything else, so we just stop. That's it. That's all we do. If you had 3 things to the right of the arrow, then you would add a third thing, and you would raise it to that power if it was there. We're going to divide that by the reactants, however many there are. This just is a generic thing that says A and B. So we do happen to have 2. We have H2, so slap that in a square bracket. Raise it to its coefficient. That's squared. Okay, we do have another one. That's O2. And then what we're going to do is put it in brackets and raise it to its power. Well, there's an understood 1 there, so I just leave it like that. This is the KEQ of this particular reaction. And folks, it's as simple as that. On the released exams, I think they have asked some questions about, just how to write it. So all you need to do is pick out of a multiple choice lineup, which one is the correct expression, remembering that the products go on top would go a long way to helping you, and then that the coefficients are your powers. Now, mathematically, if they should ask you about the meanings of KEQ, and you have to think about the formula, okay? So if the KEQ is greater than 1, it says the products are favored. So let's look at this for just a second. This is a fraction. So that should make some pretty good sense that if the top number is larger, in a fraction, if our top number is larger than the bottom number, then you're going to have an answer that is greater than 1. So that means that these things on top happen more often. Likewise, if KEQ is equal to 1, that means that they're equal, because again, it's a fraction. So for a fraction to equal 1, then the top and the bottom have to be exactly the same. I guess the way that we could do this one is we could draw it this way. Like if the top one is big and the little number is small, it'll be greater than 1. Well, what if it's less than 1? Then that means the top number is small and the bottom number is big, because in a fraction, if the denominator is bigger than the top number, then it comes out to be a number less than 1. So you do need to be able to interpret the meanings of these as to what's going to happen and what's going to be favored. Now, if you go on in chemistry with college, you'll actually put the numbers in and compute this. Okay. It's practice time. I'm going to do a bunch of examples. So if you have doubts about your ability to do this, then stick with me. What I'm going to do is answer all of these, and I'm going to write the KEQ for this, okay? So first of all, if we decrease the concentration of dihydrogen sulfide, that is this. So if we take this away, it's going to want to put it back. So then that means it needs to shift to the left. It needs to head back in the same direction to make more of it. Okay, all right, what about if we increase the pressure? We can do that with this because everything's gases. Well, okay, I know in my head if we increase the pressure, then I'm going to want to decrease the pressure. But the question is which side has less pressure, because that's the side I need to go to. Well, this side has 1 plus 2. This side has 3 moles. This side has 1 plus 4. This side has 5 moles. That means the 3 mole side has less pressure, so it is going to shift to the left, or you could also say shift reverse for both of those. Okay, what if we increase the temperature of the system? Now, okay, on this particular one, I'm going to say let's just skip it because I don't have heat written up here, and we don't know enough about the reactions in order to answer that on our own, or I don't expect you to at this point, so we'll just skip it. Okay, what if we increase the concentration of carbon disulfide? That is this stuff. We make more of this. Well, how's it going to fix that? It's going to make less of it. Well, which side doesn't have this? Because that's the side with less of it. That would be over here. So what's it going to do? It's going to shift left, or you could say reverse. Okay, well, let's erase some of this stuff because it's getting busy. What if we decrease the concentration of methane? Well, this is methane. So what if we take this stuff out? You know, take some of it or all of it. Well, we need to put it back. Well, which side is it on? It's on the left side. Then guess what it's going to do? It's yet again going to shift left or reverse. Everything we answered for this one shifted to the left. It's just how it worked. Okay, now, unrelated, let's write the KEQ for this thing. So the KEQ, all right, we know we have a fraction. We're going to put our products on top. So here's the first one, CS2. We put it in square brackets, and we raise it to its coefficient. Well, that's a 1, so I write nothing. Put the next thing in brackets. That's H2. Raise it to its coefficient. Raise to the 4th power. Then we put it over the reactants over here. That's CH4. Raise it to its coefficient, which is an understood 1, so we leave it. And then put the other thing in square brackets. That's H2S, and raise it to its coefficient. Oops, sorry, that's a 2. I wrote a 1. So we raise it to the 2nd power. Right there, that is the KEQ. Let's try some more. Okay, what about this one? What you could do if you want to quiz yourself is pause this, try it yourself, and then unpause it and see how you did based on my answers. That's what I would do before I take the quiz. Okay, if sulfur dioxide is added, well, this is sulfur dioxide. So if we add more of this, we need to make less of it. So where is it not? It's not on this side over here. It's not on the left. So it is going to shift left or reverse. If we shift to the right, we just make more of it, and then that doesn't help anything. Okay, what if sulfur trioxide is removed? That's this thing. What if we take this out? Well, then we need to make more of it. Which side is it on? Because that's where there's more of it. It's on the left. So yet again, we are shifting to the left. How funny is it that everything I've chosen shifts to the left? Oxygen is added to the system. Well, that's on the right-hand side. So if oxygen is on the right, so it's right here, then we need to make less of it. Well, then we need to head to the left. Wow, yet again, it shifts left. Okay, if I ask you pressure questions with this, which side has less pressure? Well, the answer to that is this side, because it's only got 2 moles. This side has more because it's got 2 plus 1 is 3. Okay, so if we increase the pressure, it would shift left. If we decrease the pressure, it would shift to the right to make more pressure. Now, let's write the KEQ for this thing. The products go on top. So the first thing in brackets is SO2. Raise it to a power of the coefficient. So that's squared. Then we put O2 in brackets. And we raise that to what power? An understood 1, so we just leave it. For reactants, we put SO3 on the bottom and raise it to a 2. We only have one thing on the bottom because that's all that's over here. Okay? I think this might be my last one. Nope, I've got 2 more sets. So, you know, if you're struggling, then stay with me. I mean, there's no harm in continued practice. Okay, so same thing, it's different question. Predict the effect of decreasing the temperature for this one. So this is all about temp for these, okay? So part of this relies upon your knowledge of the Q stuff. So this side has the heat. The right side has heat. So if we decrease the temperature, we need to make more heat. We need to increase it. Well, that means I need to point to the side that has it. That's right here. So this one is going to shift, holy cow, the first one to the right. All right. Now, what about B? Well, here's the tricky part about B. B doesn't put it in the reaction. Well, you should know from our previous module that if it's positive, then it would be written over here in the traditional reactant position. So that means 37.2 kilojoules is going to go in with 2 moles of NH3. So if it gets written on this side, then the left side has the heat. So if we decrease the temperature, it needs to head towards the side with the heat. This one is going to shift to the left, our most favorite answer. What about C? Well, you should also know that if it's a negative, that means it's written on the traditional product side. So the right side is the side with the heat. So if we take heat away, we need to make more of it. This one will shift yet again to the right because it's shifting to the side that has the heat. Now, I'm not going to write the KEQ for all of these since each of these had a different reaction, okay? Let's look at the last one. So for this one, it says, what happens to the position when these changes are made? So what if HGO is added? So we put more over here. Well, what do I need to do? I need to head to the side where it's not there. So this time it's going to shift to the right because that's where it's not. What if the pressure on the system increases? Well, since it's asking this question and not everything is a gas, pressure only affects the gases. Well, there's gas on this side. So what that means is that this side is going to have pressure and this side will have less pressure. So if we increase the pressure, it's going to want to head over here to the solid thing. It'll shift to the left because, you know, it's heading away from the gas. So you can do this if there's only one gas present. The first example that I showed you didn't have any, I don't think. What about the KEQ? Well, put the products on top. We're going to put HG, raise it to a power of the coefficient. It's a 1. And then O2 in brackets, raise it also to a 1. And then HO is going on the bottom, but this one will have to be squared because it has a 2 in front of it. Now, if you had trouble with these, you can either watch the videos again and pause as you go. You can certainly do your practice problems. You have quite a few of these to practice answering the shifty stuff and the KEQ problems. I wouldn't be surprised if this was one where people needed me during office hours or had some questions. So feel free to get in touch with me. And again, don't take all of the quiz chances without asking something of me or watching the rest of this.